Okay, so this is very important to understand. So I'm gonna try to go back to paper for the best one to use as a policy note. So if there's the medium's blank, it doesn't matter. If someone's having some idea, they should have the plain one, and the rest one is the fair one I'm using to prove it, because I'm proving something now really important to myself. So this is a 30 minutes timer. So basically, guys, I'm gonna show you something I'm gonna do, but it's gonna use my framework of lambda calculus, what I call integral calculus. Because I got one question. So basically, you got the Laplace transform, which the symbol is the Laplace transform. But we're gonna watch this video, but we're gonna solve this problem out. But I want you guys to really understand in problem, because you've got the model already. But we're gonna look at it from an angle, because that's always one we'll be using. Because if you guys give it the wrong ones, it's gonna be getting funny. You can mess up the whole thing. But it's my model of calculus problems for real world intelligent problems. So I got it here, and I'm gonna start now. Okay, where do I start? I can look at my face now. Oh, that's my face, I'm here, I'm still the problem, just blanking the paper. And I'm bored because you don't have to ground it on. So it's just paper. So this is the bare minimum you need to start. And a pen, that's what you need to start. It doesn't matter. Everyone has the still room. Any problem they want to do. It doesn't matter how big the board is, but you have to have the equivalent time. If it's this is policy now, because it's a still room, it can work in the still room, because you have something to look at. And it doesn't matter. This is a pen. This pen is red. It's red pen, but it's like literally red, because I love red. I don't love red. I just found a pen, but I just pick a pen. I got one pen, and I got simply two of this, because it's just a simple thing. You have a backup one, outside the room, because you're in the still room. Two in your still room, because you're emergency. As an emergency, you get one outside, all sparse model. Okay, thank you. So what I'm saying here, so we got this is what is that? What is so this is a legislation. So we got this the right route, but this is the right route. So I don't really want to describe what I'm doing, but because I'm no masking, I want to show this everything's following the standard procedure. So we got something called the Laplace transform. So the Laplace transform is this simple. Okay, now I don't want to draw it. Let me draw it bigger. Let me draw it bigger because my screen. So I agree. This Laplace transform. This is simple for it. This is simple for it. I don't hate it. I hate it because it's kind of masking. So this why it's to me this symbol is equivalent. It's like the lambda equivalent of so if you use the lambda equivalent of this, but this is like so this symbol is the lambda equivalent of half a third, so half a system, half a solution. So this is half a solution. Everything this is it doesn't matter what's integration or Fourier series. What the problem is, this Laplace. L for lambda, A for alpha, P for papa, A for alpha, C for Charlie, E for echo is basically having an area. Doesn't matter if it's a curve or signature. It just solves half the problem. It doesn't matter for space and time, because if you have half the energy, you have to have the time to do it. It solves half the problem, and this is what I hate. Because it doesn't evolve. It doesn't solve the full problem. It solves the problem for half the resources it has, and that's why I hate it. It doesn't matter whether it's integration or not over the area. It's linear. It's still linear. So this is why I see. So this symbol is like this is what you guys are doing when you solve problems. Fully, you have two solutions, two integrations. But this integration can be reduced to one thing. So this is two integrations. So this two is equal to my one. So this is my one. So this is my one, because I just flipped it. Why did I flip it? Because I'm smart. I think I'm smart. No, because I'm trying to represent your 2 to 1 my 1. Because I flipped it because it's a Fourier series. It doesn't matter what it is. It's dynamic and it can evolve and can be 1 and 1.5, and it can be sparse. It just doesn't. It's not linear. It doesn't make sense. Because you guys work hard, but you don't work hard enough. You work at your own time, at your own pace, and it's annoying me because you don't really want to think about the problem from your ontological angle. So basically, I'm saying that for me, I see your problems. It doesn't matter. So say you see this area, this sheet of paper, this area like dots, dots. The heat propagated. It doesn't really matter to me because 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 2, 4, 5, 6. This 6 here is literally areas of heating spaces. But this 6 things here have to heat up to get to the other end. But the other end is like other end of the shape is like it doesn't matter the structure. Whether it's like what a sheet of glass or the okay let's remember solids.
solitude. Basically, you got a solid, so you got a solitude. So whether the solitude is like the material that's hard, solid, or plasticitude, because I want to do it properly. Your solution is just always do halfway. It's kind of annoying because whether it's energy or anything, it doesn't matter what it is. So plasticitude, plastic energy distribution. If this material is plastic, everything is formed as plastic, and that's plastic energy transfer via plastic medium. Because it actually makes sense to me. Because if you start a point. If you hear, basically, this is what it is. Basically, if water boils 100%, 100 degrees Celsius, 100 degrees Celsius is what water. It has to propagate to the other end, other area, but the surface area, which is a problem with the plastic one, because the plastic does it quicker, because plastic can melt, but if it was meant to contain the water and the volume, so you get 100 degrees squared, 100 degrees cubed, that would be 100 times 100, which would be 1000, 100, 100 power of 3. Which would be 0, 0, 0, 0, 0, 0, 0. That would be 0 to the power of 9, because you got 9 zeros, 9 sets of zeros. But it still doesn't preserve that pressure. It doesn't. You don't think, guys. You don't think for yourselves. Basically, you don't think about the one. You think about the what is the problem, yes, but you don't think about how the consequences of not finding resolution is. Even a bad memory. You don't think about what you do, the structure of the problem. Sometimes you even don't think about structure of the problem, because it's kind of annoying to me, because it doesn't think. So back to my problem. So I don't want to talk about this plus. So everything that's called a plasticitude is literally a plastic equivalent of the medium. So medium. The medium is what? Doesn't matter whether it's a silicon is ice. The silicon is if it can propagate electricity, if it can propagate of dynamic field. This is the model we use. I'm trying to do this now. So we get the AB. So halfway, A divided by A. So you get a Hamiltonian Eulerian graph cycle. You can model this based on the dynamic waves of waves, how they move around mediums. So you got a plastic, but you got solid. So you get a solitude, because it's a solid medium for all solids. It is a solid, but you get that chemical type. Plastic, you get plasticitude. You get a plasticitude. Sorry. For air, you get because you have to use the formal term, because solid, water, liquiditude, because it works in liquid. So basically, you can solve the problem for this one, Nandi. But I don't want to solve it because I'm tired. But I'm going to give the formal framework here, because it's basically a pass. So I'm writing it down because I'm giving you guys the formal without actually giving you the jargon. So A and B, between, let's see, if you get something that's 100 starts at, you start at point 180, is a stop, you get B is an end, but B is an end is a stop. If you want one way, you can just B is an end, so when you just complete this for one way, you don't complete for, basically, when you commit for one way, you commit for stop. That means you start to end. If the content does just come back to start, because if you come back to start, that means the system's stable. So everything must be to start. It doesn't matter, because if the system dynamically fails, halfway, it has to restart. Because halfway is like a restart. It has to continue, and that's the restart. It doesn't matter if you have something that doesn't restart, that means it failed. It bugged out. It's clashing, and the time you get pi r squared, and that's pi squared. Pi squared standard one. You get a 2 pi r. 2 pi are just perimeter, but the perimeter is not enough. So your things are always perimeter bound. If you get a solution, because you're trying to go from A to B, B to A, but you don't think about the area. You don't think about the long-term effect of the parts. How many parts can take the sparse part, which is the policy known as sparse solution via path first integration first based on the medium, because the path of the medium is just a chemical path. It's the size space can explode, and that's all our paths. Because it doesn't matter who you are, what you are. You have a path, but your path is your space and your time and what you want to do. Which I'm saying is your path. Basically, your path can be my space. This space from room. This is your space, because you guys can stay in this room, don't study human rights. But this is not my space. But this is not my path either. I took this space because I shifted my consciousness. I shifted my way of. Basically, I'm autistic. I'm a spectrum, but I'm trying to give you a form of. So A, B. So basically, this is a branch. This is a branch B. This is A branch. This is like a path, but this is a branch. A branch is like a path. All paths we take, but it's a branch because it's a path we can take. This is your space, and this is my time. This is the path we take. This is the area we take. This would be 45 degrees plus 45 degrees. 2 pi r. 2 45 degrees is 90 pi r. Oh, I got a calculator here. 90 is 90 is the radius. 45 degrees, 45 degrees. 90 degrees, degrees plus 2 pi r. 2r. So that's 90 degrees times r. I've got my calculator here, guys. I can do this with a calculator. 90 r. all American countries are banned. All exported goods for tools are banned. So that's 90 R. 90 pi. Okay, so 90 pi will be 228 degrees, because that's 90 degrees. You get equivalent one in the path, because the edge is the path. Doesn't matter when you fit it out. You have to come equivalent in the physical world. Because you are, if you're in your head, you have a physical form. Doesn't matter who you are. If you're too physical, you have one physical, because it's past topology, and that's the policy of the system must between you, whether you're in a physical, metaphysical, physical form. So you have a physical form, form, unless you hand your fingers, or your fingers away, and where you want to go, and your physical, based on how you want to do something. It doesnesn't matter whether it's auxiliary or not. What you want to do, everyone's ontologically bound. So you have a pathway, the branch, everyone's a branch. Everyone's a branch, who's a way, the path, the way it could be the edge, or some kind of time they want to do something. Time to think about, thinking space is my time to, because you know what I'm saying. So space and time bound. So everyone has a space branch and a time branch. And that space branch and time branch is a way to go, and that's their way to go, my way to go, your way to go, and you got what pathway, very way shape, like the physical shape or the mental shape of our consciousness. Based on lattice disjoint. Now, lattice disjoint is very important, but I'll come back to that later. So that's what I'm trying to solve today. Lattice disjoint. But the space shape, way, shape, and form. Way, shape, and form. Shape. Because how we are allows us to be. The circle does not fit the square, because it fits a triangle, because you can't take a circle and make a square. Because that's just kind of balance, because you never. This squares in my framework. Those squares are put there. And the band, so if you see in squares, you have to transform to a triangle, some way, or shape or form, and you have to describe it. So, obviously you got this. So, and that's equation evaluation. If you use a square to compute, because if the completion, if the completion means a rigid edge, that's equation evaluation. You have to you can pop it easily, because you have 4 edges, but 4 edges that literally can be molded to get. Basically, a square is hard to shape. It's impossible. It's so rigid that you can shape you can get a computer square from a triangle, but it's so hard. It's so expensive. That's why I'm banning squares in computation. It may sound crazy, but if you have a square, circle is from a square, you have to compute the edges of the circle. But you have to compute some kind of arbitrary numbers that you don't even know how to get, because it takes so much space and time in your frame of mind, in our universe, to get, and that's why it's banned. Because I don't ban squares because I hate them. I ban squares because there's so much problems, round edges. Because that's why I ban them. Even like a small edge can lead to compute that growth of a what else? So today I'm gonna solve the problem via Fourier series, but this is one integration. So this is your one, but I'm not gonna solve my one. So this is my one. So your two one. So your two is my one. So this is like your two integration is my one. My one left. Basically when you're going. Basically, what I'm saying to you is like I can shift the plane of existence here. So it doesn't matter the path you're going. Your two clockwise or right rotation is my two left. So it's my two left. Your two clockwise. So if you go clockwise, 360 once, 360, you're 720. You're back where you started. Where you're going, you started and you ended. You are already. Your two rotation clockwise. No, so your two rotation clockwise is my one rotation, and anti-clockwise, because I already know where I'm going, because that's why you see, because it doesn't matter how slow you guys. That's what I'm saying, because as a policy, that's what I'm seeing. So 360 times 2, 360 squared. So basically, if it is over 360, you got pi r squared. You get 2 plus 2 pi r. But every time you rotate 360, go 90 degrees, 180 degrees, 270 degrees, 360 degrees. That's what I'm saying. You get a path you can take, and a path you can all take. But when you guys are going, you guys don't know what you're gonna do, because I already know what you're gonna do before you do. And that's what I'm saying. I know things that you don't know ahead of time, because I already know what I'm gonna do. That's what I'm saying. Because I think I'm smart even because I already know what I'm doing, and I can see what you guys are doing before you do, because you don't know what you're gonna do yet. Which I'm saying is the policy of my framework. That's what I do. So this is why I already know the shape of things. The outcome of things. I'm not telepathic. I just really know. If you really know, and that's what I'm saying. That's what I'm saying. Is really what it is. Okay. Let me start. So I'm trying to use this the Fourier series to compute this number. What is the problem? The problem is this problem here. So this is a problem here, very important problem. So I'm gonna watch this video. I'm gonna show you the problem I'm gonna define here in a minute. But let's watch this video, okay? The beauty of mathematics.
2 lines on this piece of paper. And suppose I drop this needle now on the paper.
Sometimes when you drop the needle, it will cut a line, and sometimes it drops between the lines. It turns out the probability that the needle lands so it cuts a line is exactly 2 over pi, or about 64%.
Now, what that means is that in principle, I could drop this needle millions of times. I could count the times when it crosses a line and when it doesn't cross a line. And I could actually even calculate pi, even though there are no circles here, no diameters of a circle, nothing like that. It's really amazing. Suppose I take this needle.
So basically, the thing is basically auxiliary. So basically, think of this as redshift. So everything's moving away from us. But why is everything moving away? That's kind of question. Why are we in this universe? Why are we here? But we're not really. We're here now. But we are moving away from things because things fall. But things fall for reasons. So things fall down. You think about it. Everything is going more entropy together, and they don't make any sense. But why is that? It doesn't matter what it is. It doesn't matter. Let's say your sense. There's like it's kind of disjoint. Of everything. Basically, if there's a rabbit here, the rabbit knows me, but I don't know the rabbit. But rabbit is smaller, but it knows more. It can observe more because it's freer to do what it does. It doesn't matter the blackbird. It's like the rabbit's like there because it knows what to do. Like it's not about rabbits I like, but because rabbits are there, but they need the space to do it. Like a rabbits, all rabbits are free because you get like a free supply because it's like some kind of space that rabbit can breathe. The breathing spaces of rabbit, but the difference is if you cut the natural habitat out, which is our natural habitat, But when they thrive, they try to, you get actual air. So you have all rabbits properly because basically all the rabbits in my position should have to touch. They should be really free in the flowers. They really come. I have a way to go because that means I'm not free. Because it doesn't matter what it is. Something that's been happening at the local level for them. And when the rabbits are little thriving, when the black bunnies and the black hares are little thriving, and I'm going to show you the policy now because I love rabbits and hens. Rabbits and hens, they have some kind of we have some kind of disjoint equilibrium. That's disjoint. So if I change my specific to a rabbit, what does that mean for a rabbit? A rabbit is a utopia. No. A rabbit's not a utopia. Rabbit is just enjoy life, because they meet the rabbit friends. It's what I'm saying, because their utopia is just our norm. From an angle, it's like why doesn't it talk for a rabbit to have a good life? Because if a rabbit's not there, that means there's something's wrong with that biome. Something's wrong. But I don't use that example here because I want to use the one I really understand mathematically. I like this one actually. Let's use this. Let's say two black bunnies. Two black bunnies to every one of us, to one human being, one me, Namdi, one man, one stick for him. But if there's two, it can be what? Four. And this will be 4 black bunnies. Because I'm seeing black bunnies, 4 black bunnies. That means there are what? 2 Namdis, let's just say they're male and female, because that's what bunnies do. Because I'm using myself as an example. That'd be like 1 male, 1 female. Then obviously, there's someone I can go to. 1 male friend and 1 female friend. That kind of thing is saying it's stable for everyone. It doesn't matter whether Namdi is there or not in the physical and the metaphysical. Whether Namdi is it doesn't matter whether Namdi is mentally there. Basically, Darwin's are there have to be there physically. This doesn't matter physically in the physical form. But if Namdi is there, that means Namdi is a path. I'm not talking about like a sexy. I'm giving like an idea because I'm giving you because it's kind of real life. It doesn't really matter as a part. You can use the real life, but you have to use the kind of thing. So we're gonna steal the bunny analogy because I love bunnies. So we don't keep myself in there no more. Only the bunnies. But the goal of this is to keep doing this. It doesn't matter a stick for this. You get a black man like me Namdi. So me Namdi, a man. So it's a black man, black guy. So I'm saying that's what I'm saying. 2 bunnies equals 4 bunnies, and the 4 bunnies equals 8 bunnies. Because they are bunnies. So that's the idea. But there's some of disjoint here. So we share a reality, one reality. So the 2 bunnies to 1. The one reality means we're all stable. We're all okay. I'm okay because there's a bunny somewhere in Biafra right now. 2 bunnies because they're driving. We do have bunnies there. We do have bunnies. So 2 to 1. So 2 union 1, 2 disjoint 1. And 1 or 2 intersection 1. So basically these are 2 spaces. So they have for every 2 bunnies there's what? 2B, 2 bunnies. We have the pi framework. So you get 2b of 2p, get like a pi r squared, so 2 bunnies. So let's do pi to what? 15 decimal places, because you know I love pi. Pi, number pi is what? 3.14. Let me write it here. I don't forget it. 3. It doesn't matter because of 3.14159 to 65. 3. 3.159 159 256. So this is kind of done, right? So see the bunny thing? See the bunny. I'm proud of it because it doesn't matter how I write it because I'm trying to get structure. I'm trying to structure my own way. That's go there. So this is the thing I'm doing for myself. See the bunny thing? The 2 bunnies are there and they're happy because we have bunnies there, believe it or not. But the kind of thing I'm saying is because they are there and they're thriving. But that means someone is happy. Someone's okay. One person's okay. I'm happy. Actually in a good mood. To actually move in their life. That's what that means. It doesn't matter who that person is. It just matters they're okay. And that's why you don't touch bunnies or touch ostriches, because ostriches can kick you. But you keep all the bunnies alone. The black ostriches, all the African black ostriches only. We get black chickens, roosters, a cow, get like rooster, get cows, you get fish, get all the fish, native fish there, and they but this they can produce anything that can produce 2. If you have just put 2 of them together and you put together, that includes ostriches. Basically, ostriches need to have no foxes, like because so you get 2 ostriches, you get 4 ostriches, for a human being, you get 2 cats, 2 native cats, not big cats, never big cats, 2 cats, you get 2 cats, you get what? 2 small cats, never big cats. You don't have big cats there, because that's the kind of thing I hate. Lions, nothing there, don't get nothing there, because that's a constitution. But we get zoos away from them, because you travel to a zoo, you're especially dangerous. You get zoos because for those wild cats and wild stuff, but never the apes, because apes are too like us. The apes can live freely in the world of Biafra. You know what I'm saying? Because you get nothing like an ape. Doesn't matter whether it's like a meerkat, things that meerkats that are fine because if you could just put 2 of them, just breed, rabbits, so anything that can come in 2, mathematically, no elephants, anything that you can just breed by itself with 2 is free, that's what I'm saying. It's just to be there because it's stable it's stable. Anything that can't be, I don't even want them there, but I have to decide them because I don't really know there for a long time. So I'm gonna come and do that research there. Wait a second. So the idea is 3.145. So 2 bunnies. 2 bunnies. So you get 2b, 2 bunnies, to 2 bunnies, to 2 bunnies, and 2 because I'm giving you a simple example. So you get 2b and you get b squared. So you get the opposite, b squared or 2b. But the space and time rules, so you get the number squared. So it doesn't matter. It can be cubed, but that means you have to map all the cubes with lattice. For example, if the bunnies are cubed, you have 3 bunnies to have one thing. Why is that stable? B cubed, you get the area dimension of b. But B is a plane. You don't need 3 bunnies to have section. You don't need them. But you just need one bunny to stable them. But it's because I'm using my reciprocal framework to prove it in the real world because I don't like the kind of racism we do for this kind of framework. So we get as a policy racism is bad, everything is bad like that. You always use people. You don't use it. For every human being, you do. For every person, you have to define this kind of framework I'm doing. So get B 2 bunnies. 2 bunnies, pi squared, so 3.4. So get b squared, and then we get b pi, b pi and b squared as well. B squared, b is 2, 2b, 2b, 2p, and that's a set equation. These are 2 branches on 1 to 1 me. So that's kind of an idea here. So what does it matter to me? Okay, so this is our axis. So we share a half reality. Half reality. So you get half reality here. For all the rest you share, we share half of it. In some way, shape, or form. This only in some way you go. You see a bunny in some form, some metaphysical form, or we share half of everything. But we can't see it because it's disjoint. So basically, that is the way. There's one full reality they have that we cannot see. It doesn't matter the algorithm you use or the space you have. Or the physical space you have, or the metaphysical. There's one full reality, one full body reality, one full one that's not a half that they can see. One full or one full one that they can observe and act on, and that we can never do that, because it's disjoint. So that's disjoint. So this is the chemical state of everything around us, because everything's naturally disjoint. So everything's naturally half, because we are ratios. Everything's naturally half. So if you can see a bunny, it can see you. It can see you fully, because it's like it's some things the bunny can see is fully because it's more of them. They know more. They know more, and they can do more because they know more. That's why you can never catch a bunny. You never catch a bunny, but you're allowed to be near a bunny. If a bunny allows you consent, consensual, you can catch a bunny, but you're not allowed to catch a bunny and run over because not you guys. Because they're allowed to hold the bunnies, but when they leave you, you leave them. Straightforward as a policy. No, don't should violate that policy here, because so that's kind of idea. That's kind of idea. You get half of everything. So they have this one. So we have 1/2, 1 plus 1/2, and that's one reality of don't 1/2. But their 1/2, 1 plus 1 equals 1. But we share 1 times a half. 1 times 1/2 is what? A quarter. So they have a quarter reality, which is equal to 1/2, 1/4 plus 1/4. Half. Will share, and they can know, and they can all know, but we can never all know, never know, because that's never know without the right tools, the right way shooting. Basically, based on some kind of path algorithm we define, based on kind of form or structure, we observe them, based on kind of space time, but being in space time duality. But then we can never know this because we don't have the right instrument. We can know it, but we can only know it at a time, at one space in time, one point of space or one time. We can know it. I know it can work, but that's the idea. We start from the lowest ice form. We start to build up our stuff again. But that's the idea. Since kind of just this is what the bunnies do. So we can extend the bunnies, space or time, which is the area they have. It's a policy now, to ensure that they can expand the horizons, and they can tell us more. They can give us more about ontology. So can we build up the short frame? That's the idea. You give them 3, they can grow like so. Just by putting a bunny in the physical world, in the physical space, 2 more bunnies because they come in 2s. As a policy, you give them 2 more pairs. You get 2, you get 4. Well, those 4 can become what? 4. So you get 4 for 2 bunnies. 2 for we give 4 plus 4, and that becomes 8. 8 bunnies. 8 bunnies. So that'd be 1/8 for us, because more realities we can observe, but it's just disjoint. So the rabbits have their own individual realities. They can tell us more, give us more about ontology. I'm just gonna go here. It's like that. Oh, what is this? Am I still 26 minutes? So what's the problem here? So the problem is this. So this is the problem here, guys. The beautiful mathematics. Okay, let's just watch the video.
So that the length of the needle is equal to the distance between 2 lines on this piece of paper. And suppose I drop this needle now on the paper.
Sometimes when you drop the needle, it will cut a line, and sometimes it drops between the lines. It turns out the probability that the needle lands so it cuts a line is exactly 2 over pi, or about 64%.
Now, what that means is that in principle, I could drop this needle millions of times. I could count the times when it crosses a line and when it doesn't cross a line, and I could actually even calculate pi, even though there are no circles here, no diameters of a circle, nothing like that. It's really amazing. Suppose I take this...
Okay, so my insight to this problem is very important. This problem is very important for 2 reasons only. Stable, biological stability, and what? Biology is a bioinformatics, biological structure, being, what is the mind or the soul? There's some kind of way the biology that a rabbit can, bunny can evolve, but safely with the mind. So the bunnies are stable. 2 bunnies here, two people. It doesn't matter what it is, but that's kind of idea here. There's some kind of stability in there. I don't care whether it's sex or no algorithms here. Just because where you can all go, we can all go, whether we are discharged or not. It's kind of this. So basically, the idea of this. So if I go counterclockwise, which is my own lapis, well, if you're going right, if one person is going right, if one body is going right, another body is going right, no left, right, you get 2 people with right hands, or 1 person with right hands. So that's 2 lapis transforms, 2 integrations, but their right equals one person with the one right and one left, because they went the right way with the people with the right hand. But there's one person that share my reality that did not get a bunny, and what did not get So if I didn't get a bunny, if I didn't get a woman, I don't really care about women. I don't care about the bunnies. If one bunny, so if you get 3 bunnies and one bunny has, if you get one bunny and they don't get to go the other way, one small bunny and one rabbit, they go left because they go left alone. Then there has to be another bunny somewhere. And sometimes to get us, just wish to add one or 2 more bunnies, one more bunny, so everyone can get a bunny. But I don't get a bunny, so those who have a bunny for a bunny, but it's supposed to be ensured that the bunnies are fine because bunnies are stable mentally and physically. So if you get a bunny, you get a bunny. You don't get a bunny, get a bunny. Get a from nowhere. Put a bunny in there. It's a policy there. It doesn't matter because the bunny has to find a bunny. In a framework. It doesn't matter. That's the idea. So you get a level. So if you go right. If you rotate clockwise. If 2 bunnies rotate clockwise 90 degrees. If 180 plus 180 is 360. But this is 290 degrees. 290 degrees is you can get the combination of 180 plus 180. When you add them, 90 plus 270, but you try to rotate 270 degrees, which is a quarter of it, because 90 equals 260, because you get a ratio of that. So you get 1 plus 1 over, so you get 4 quadrants, but this 4 quadrants is like a 1, but this 4 quadrants is a 2 over 4, 2 over 4, which is 2 over 4 as well, a half, equals to half. So you get a half quadrant shared between 2 people, 2 realities, and 2 realities can be 4 realities, you say. One in a full whole, and this is kind of stability and framework I'm implementing here. But biologically, so there's no problem. So it has to happen over the 10% rule, because growth is happens in increments. So 10%, if you exist something 10%, it's not stable, you pop down. This is my anti-pop protocol for like my operating system. So my anti-pop protocol shows that I can't pop. So basically, if my OS fails, it fails because I done something wrong, but I didn't want to fail that. So the kind of thing I'm envisioning is this kind of video maths. So you see, basically this man, he did it right wrongly. Basically, the lines are meant to be. He doesn't know this, but he made a mistake. See these lines? They must be according to the paper, because this paper is the whole field of the system. So if this wasn't the whole field, he actually can't. You only see the lines, and him seeing the lines is what he's using to measure his output, and that's what the big failure in his framework. He's failing because he doesn't have the lines drawn precisely. So if there's like 100 centimeters, it should be auto. The bare unit should be everything should be 10. Everything should be 10%. So 10%. 20%, so 30%, 40%, 60%, 60%, 70%, 80%, 100%. So this is like 10 lines. Because this one's like this is a needle. You get 10 lines of a needle, and that's the problem he has here. My pen just ran out of ink. It just ran out of ink. So this line is what I'm saying. It has to be or linear. So if you learn to draw, so policy everyone wants to learn to draw straight lines now as a policy, because Okay, so get the my parents working again. So get the lines there. But this is this is your 10%. If you have 1%, we can share any path we take. 10%. If you start from the other end, get 10%, 10%. But we share what? A 10% here, but it just takes time, space and time, to get from here to here, to the center of the 10%, which would be our 10%, our 10%, our stability. And that's the problem of the system here, really. So, you see this thing? You didn't understand what you did, but, it has to be equal. 100% is too bad for this kind of thing. So, 100% is here. You get 100%, you don't want to lose any potential. So, you go your way. It doesn't matter where you're trying to. So, if you go in here, you go anywhere, but this is like a grid. This is a pathway. This one is basically you get this grid. It's a grid because it's a lattice of energy. So you get 10% for everything you do. So you get 100 by 100 grid. Based on unit model. Unit model is just the unit system. So you get this one. You get the other one. This can go this way, but this is a bit harder because this is like a triple lattice integration. So see this people? He has it's split to 10 segments, 10% of everything of the unit model. So he's doing it wrong, but he doesn't understand what he's doing because he's just making the maths funny. Because he's taking the wrong measurement because the lines. What you can see is the whole paper. I can see the whole paper too, but I'm taking the right measurement. I'm taking the right measurement of my system because my system allows me to do so. Oh, what is this? But let me just save this, guys. Let me just save this. I'm kind of recording. Pi. Sorry, guys. Let me save. This is 32 minutes. Basically, it's past 32 minutes. Let me just save pi export. I think I just do pi the WAV. And that's pi the WAV and file new. Pi. Let me see this again. So this is pi export. So basically, the kind of thing is basically you have to map the system. It doesn't matter how much you put a data rate. Basically, you have some algorithm you define. It doesn't matter. Basically, the goal is literally have some algorithm defined. What we call deterrent. So basically, any deterrent check is as a policy. It doesn't matter what. I'm going to go to explore system. So you're going to explore your way. How you go. It doesn't matter how you deterrent. Okay, find this part one by one, and then define some area. But you have to define some areas of policy. So if you want to define this area, you can start from the literal integration of each point. You have to define this one units of area, and then you can copy that area. So you can, if you define this, you can find all the area of your universe. You can do. You can find all the area of this one, based on the y, x, and x, y, and you have all the areas you share and I share, y and x and y axis, and then you can get what a grid, a path you can go to, and the path is the way you go. Computationally, literally, it's just what it is. You're stable. Like I'm computing it now because I want you guys to have it. So you get an x. So if you get an x coordinate system, you get a minus x. So if you get an x coordinate, you get a minus x. But the minus 6 is what? Not stable for you. Your instability to women or men, it doesn't matter. The body is what? But you have a y-axis. So you get an s, you get a y, you get a plus y, you get a minus y, you get a minus y, you get a plus y. So basically, this y plus y, this minus y for me, this minus y is unstable because I cannot see it. I can't even see what women think or women do. This thing is serious. That's where the disjoint happens. The integration disjoint. That's basically. But if you don't know about it by your own insight, you don't really need to know about it. You need to care about it because you just based body's reality here. That's the idea. Because we share a 1y xy. Basically, we share a chemical x. So your x-axis is my minus x-axis. Your minus x-axis is my x-axis, and my y-axis is your minus y, but I can never see your y-axis because it's just observing your state of mind. But I don't have the full. I can see it. I can see you, but I can never see your your minus y-axis, and that's kind of thing. You can see both mine. So my goal is like so what makes basically this y represents the integration of the Laplace. So this is what it means. Because this is what the disjoint is. So the idea is like it doesn't matter who you are, what you do. It's computational because we can do it. So if I compute you ahead of time, that's what my ES system going to do, because they're meant to be you. But this, I'm not really seeing the ES systems here. The problem, I'm seeing them. I'm computing this because it's like integral calculus, so I can never see that Y. No matter how I try to see you, the physical, or I can't see your metaphysical you. So you get a plus, you get a your minus plus. Your minus and my minus one is your full metaphysical. This is the metaphysical you, and I can never see it. Oh, I just put a line. I cannot see it. I'm not allowed to see it because if I'm allowed to see it, then it doesn't. You can see my xy, but if I let you see it, that's what we call s minus. But you can never see because your plus is my minus. That's kind of the operator's desk, which because as a plus. So what am I talking about this, Robert? So. 2 to 1, but the 2 to 1 mapping, 2 to 1. We go 2 to 1 mapping. So, did I start this already? So the 2 to 1 is this. So you get two realities you share that we all share, and we'll get. So that means you get one reality we'll share, and that's your physical reality, one physical reality. But that's 2 realities in total, to your 2 senses. But basically, open sense room of 6 times 6, 7 times 8 times 8. No matter who it is. Okay, I'm gonna go back to the thing now. For every 1 something, you get 2 of it. For every 2 something, you get 1 of it. But it's disjoint. That's the idea. For every 2 something, you get 1 of it. But we share that space. We share that space and time. You get that space and time. No matter what, this area. Because you don't share. Basically, you share a point. You share a part. This area. This is disjoint part. This is what we share. The space and time between it. So this is where the disjoint happens. This disjoint happens. So for me to express it mathematically to you, I will have to define this grid, and that's what the grid has come. So I will define the grid. So let me define it here. So we got the line here. I'm messing with this model. See, tomographically, the error is stable. Because no matter where you're instable or unstable, you can get stability. And that has to go here. It's mathematically certain. Because I'm a mathematician, I really don't care. And this insecurity is outside. Anything you go, doesn't matter. And the computer can help you do it because the computer can help you do it. Let's go to the AI system to assist you in your day-to-day living, everything you do. I don't really like the women here, but they're kind of bored. This kind of mathematical competition. Because the world we see, no matter if you can grow your bubble, you have more. You have infinite sets, and same thing you can get confusion. So you don't know where you're going. So this kind of has to ground you first. In BFS, you don't run away to any Japan and forget people, and then that's the same thing that happens to people. A lot of people. I'm saying to you, it doesn't work on magic. It works on mathematical principles. To me, because I'm a genius. It doesn't matter if it's software or not. You have to way you get out. Pathway what you can do to get out, no matter what you're doing, you give some new objective, you kind of cross the system, because you don't mask, basically, you don't shift your access, you don't try to rotate your mind or crack yourself to become a mind, you just change your purpose and your objective, your produce will be your new order, and that's the part you're going to do, you're going to try to change your objective to get a new area, to see more from less, for less, because if you see less, that means there's more to see on the other axis, you already see more. Other things, so, I have to say this now, if I get it wrong. So you get the neutrino, which is like the physical mass of the mental mass. It works the mental mass and the physical mass in form, weight, and structure. Anything that gives you mass, the neutrino gives you mass. Only mass. That's gravity, and it grounds you. It's just things that ground you, so you never pop, you never break. And what you get the neutrinos, and what you get the Higgs boson, which is the wave equivalent of the neutrinos. That's like they propagate waves, but they are a waveform. A kind of cool signal everyone can understand. No one's every system uses because it's a kind of cool protocol. That's why you guys put in there. You can get it. You see this here? So finally, let me define this. So you see this kind of thing? Guys, I need this properly now. So this is what I'm saying. So I'm gonna try to do it properly now, but I'm not gonna use this brick. So 0, 0, 0, 0. Let me try to do it. So the problem to solve really is this. So this kind of problem here, the
needle, so that the length of the needle is equal to the distance between two lines on this piece of paper. And suppose I drop this needle now on the paper.
Sometimes when you drop the needle, it will cut a line, and sometimes it drops between the lines. It turns out the probability that the needle lands so it cuts a line is exactly 2 over pi, or about 64%.
Okay,
now
try this out properly, because 2 over pi is not what I think it is. 2 over pi, what? 2 over pi is what? 0.6366197723. So that's like what? 64%. So if I divide this by plus, then I just have to add this one to a pi over because you don't have to add it because it's addition. So pi plus pi over 2, and that would be oh, so we get plus pi equals 2. So basically pi over 2 plus pi over 2. So plus pi over 2 is equal to so basically let me write it. So you get pi over 2. Because I get a number I didn't like, so pi divided by 2, that would be pi over 2 is equals to 1.5707 usually 1.570796326794 to 15 similar places. So basically you got 2 over pi plus pi over 2. You got basically 2 over pi is what? 0.6368. Listen, let me just show you guys. I like to show you guys things because you guys are intuitive like that. So you get these two numbers there, there. So you get the numbers. You can always see them, but you're just working on pi because I can now tell you other things too. But basically, these two numbers are very important because they work on the structure of a universal bubble. So you're moving over pops because you're working on pi. You just divide on pi. So you divide anything by 2. Half. If you have half of something, that means you are imploding something. It doesn't matter if it's a grenade. That is imploding. If you half an explosion, you get nothing. So basically, if something's exploding, it's pressed out. If you half the explosion before, if you have the space, if you have the time to halve the explosion, you hold it and it explodes in your hand. But it halves the explosion. It starts to halve the explosion. It starts to implode. You implode. You never explode. You implode in inside, and you never get a shock. It explodes, but it's nothing there anymore. There's nothing to destroy. It knows your hand. It's the kind of thing I'm trying to build. But it goes down. It's like you hold the grenade, but it explodes in your hand, but it doesn't explode you. So get the idea. Because the force is equivalent. The kind of equivalent is there because you get everything that's exploding has a space it holds and a time it can explode, and that's kind of like the thing you gotta do. You gotta keep it never explode. It doesn't say it's possible, but I don't want to talk about it now. But so you get a 2 pi r. 2 over pi, I get plus pi over r. But you guys, if you get a Fourier series or sine wave, so what would the sine wave? Basically, you get like the sine wave of this. So the sine over this, I'm trying to give you the sine equivalent of it here. So get a sine equivalent. The sine will be so the sine equivalent 2 over pi will be so let me just get my ratios down because I have to get this ratios down once and for all. So we get 2 over pi 2 over pi 2 over pi is 0.636619772367. Pi over 2 is what? Pi over 2, pi over 2, pi over 2, pi over 2 is 1.570796632679 pi over 2 and then 2 pi r, pi squared. Now pi squared is what? Because you get pi squared. Pi times pi is what? Pi squared. Pi times pi is what? 9. So 9 plus 8698 9 point basically pi squared is like the area of pi alone. What I call unit pi the kind of space a system holds is 9.8 9.869604404401. This is just constants you have to preserve. Doesn't matter what's your direction, what you set it up. You have to preserve the state of this constant. So you get to pi is 2 pi r, and then get pi r squared. But you get the ones I really like, which is the 360 view. Because you get the 2 pi over 360. Basically, you get 2 pi r over 360, and that will be the unit over the space way you physical form. You get a 2 pi r over 360, but you get the 2 pi over 180. Because they show shear 180, because 1 is a to b. So you get 2 pi r, 2 pi r, 2 pi r, 2 pi divided by over 180, and now basically gives you the ratio that you already have to preserve. So this 2 pi over 180 is what? 2 pi is 0.0174537. And that's the pi, and you get pi and pi squared. 2 pi. So you get that much. So basically, this is the ratio you all share. It doesn't matter who you are. Oh, no, this is 2 pi. Now this 2 pi is what? Pi squared. And you get this pi, so you get pi squared, 2 pi over what? 180. And this would be over a path you go over 180. Oh, no. So you get to this 2 pi of 180, and you get 2 pi, which is like and you get 180, because you can get over the stage over 180. You have to use the 180 as a so if you have two left, if you have two right axes, 2 right rotations of a pi from you gain right. You have to take 2 left to go back. You have to just turn around, but you have to just turn around. But turning around is too much effort. So you just walk back, but you don't see where you're going. You can just be back where you are, but you don't see where you have to go. You know where you're going, because that's the thing. You know where you're going. You have to go another axis. So you can either go, you cannot see where you're going, but you have to see. You have to get another axis rotation, or you can shift your view entirely where you're gonna go, because your view is basically where you're going home back. You're going back right in front of you, but you just shift your plane. Shift your way of thinking, and you be there. This thing, you shift your sight. What you're looking at. We don't even. The goal is never to change your way of direction. The goal is to be there. Be at B at A. So you have to shift your axis. As opposed to that, your y axis, your xy axis, and that's what you're gonna do. You don't shift anybody's reference point. As opposed to basically, if my y axis is your y x, if my y axis is my integration, that would be your your minus x axis. My minus x axis, your my minus epsilon, which is my epsilon axis. I'm looking up, but I don't know that, and so I'm trying to find that. So I have to change my y axis, because if I'm going to y, if I'm at y, point B, I'm actually going back to point A. But point A will be what? Another axis of yx. So y x will be 2 xx xy yx and x, but they're all plus, minus, all the combinations of the equation. But we just stick to the axis of xy, yx. So that's what the Laplace represents. So I don't have the left. So my one is like a left because I'm going backwards. I'm trying to see what you already know, we don't know, and that's what you think about neurodivergent, because I am neurodivergent. I'm probably because I know where I'm going. for example, so come on, this is my notes, guys. This is what I'm trying to build. So this is my security model, because it's literally this kind of flying model. Because if I share a safe space here in my reality, it doesn't know your space. So in the worst case, you cannot share it. The best case, you can never share that space, because because that's my reality. That's what I hold on to, which is possible. Can I do that? People don't know how to do it. So it's what I'm saying to you, because the grid is like a liquid, a lattice. They can polarize them. So it's like an X coordinate system, X Y. But if I go to this plane, I'm just system active. No matter if I start from here, I'm stable here, 100%. This is 90. If it's my 10% to the opposite. If I share goal, if you share one YY reality, a physical and mental, this is my YY, but this is your. But I'm 10% of my YY. I'm 100% of my YY. Because I really know what I'm doing. I'm really where I'm going. 100% of my YY. I have all the physical space and time. I have to be 10% stability for our space and time. Because these two people share, dynamically or not. That's what I'm saying. So the kind of physics I'm saying is important. It's just this rule. So the axis integration. So within the Laplace transform. So the Laplace transform is important because it allows you to ground yourself. So I'm gonna give you one more paper, Namdi. I'm gonna try to do it properly now. Let me just stop this thing. Lapis the Wav. Lapis the Wav. So we get Lapis the Wav and we get. So this is like a thing I'm doing. So we get this one. So basically, this doesn't matter where you go left or right. It's just like you have to show that you can stop and you start the same way. You have to come to a full stop before you come to a full stop. That's the kind of policies thing. If you stop, if you're going somewhere, you're wasting the energy. You have to come to a full stop. A maximum stop. You have to stop, just stop, a point stop. And a space stop in space and time. Then turn, because that's more energy, because you turn, and then you can come back, to your reality. That's kind of idea. You don't just warp anything, because this will be a warping of your reality, and that will distort your brain and your space time, and you still lose time because that's what you lose. You fragment your mind. In design of the system, whether you're teleporting or not, you have to work in a signal, work with the framework of polarity. So that's means the Fourier transform. This is what I call a lapis. A left lapis, a Fourier series proof. Fourier series. What does that mean? So we get a polar axis. You get Katoa. So the y x y z z. The tangent line is the parameter. So when I have a tangent, right? This is a tangent line I measure, but this is my y. This is basically your y. Because you can. This is your y. Your full y. I can see your full y axis, but this is your this is y. This is z. So you get this z. So you get this axis of z. So the tangent line is like the parameter. You can see basically tomographic. So if you measure the tangent line, what? So Katoa, the y is over run. So opposite of a hypotenuse, I get a tangent line here. So opposite sine equals opposite of a hypotenuse. This is opposite. This is y-axis. The sine y, and then we've got a cosine x. But x has two inputs. X can be what? A polar coordinate system or what? Because it doesn't matter what lattice. It doesn't matter what it is. It takes two types of inputs for some set of equations that maps to some kind of coordinate system. We use a model via sparse topology, tomography. So you can get, no matter whether the condition is the condition system or the polar system, you get that some kind of absence, and that's what you want. Always. It doesn't matter. Whether it's but you get that's where the lattice matters. This joint lattice matters. You don't want to even know. You just want the computer to tell you where you are in the world. What is Cartesian? You know where you are. Doesn't matter if it's polar or not. You get some kind of Cartesian equivalent based on the field equation, the field you're already in, and that's what the Fourier. What is the signal? You get a Fourier. What is an analog signal? You get a full analog signal. You get you get a full analog signal in a polar system. You get two ways of doing stuff to be stable. No matter where you go in the universe, it's literally the same thing I'm building for life for myself. So sine equals okay. So what does this mean? So what am I trying to do? Fourier series. A Fourier series is like Fourier series is digital equivalent Okay, a function is a tripart is a bipartite differential equivalent of an analogous sequence. So, for obviously you get for a Fourier equation of a Laplace left Laplace, you get two right. If you have two left, if you go two left, you get one right. You know, you have one right equation. You can do. If you get two right equations, you have one equivalent equation. This is what we call simultaneous Laplace equation. Basically, I'm trying to define the simultaneous Laplace equation now. Laplace equation. Laplace. Let's come down now. So the idea here, so we get 2 over pi. So what's my friend now? I got my mismatching now. It's kind of annoying actually, because I didn't really plan on it. Mismatching it. Kind of annoying. But it's this this is not what I want. This is what I want. Listen to this one. So every 2 left rotation, if you rotate twice, or if you go to 2 left hops, anything you do opposite something else, you get 2 you get one something you can do that makes it easier. Via Hamiltonian Eulerian graph rotation. I'm not trying to use Hamiltonian system Eulerian system to do it via hops. But you know, because I love hops, body hops. So I'm trying to the antipart problem is really this. Okay, 2 over pi is what 64%. Let me just try to do it now. Same thing. Let me try to compute it now. So my cost is 2 over pi. 2 over pi is what? 2 over pi. 2 over pi is what a constant pi is half pi. Let's call it half pi. Half pi, because you know it's half of pi. It's half pi. So not 2 over pi, half pi. We get 0.63661. And that's easy for me. And that's basically the half area. Get pi over 2, which is the so this is called a unit perimeter. This unit because pi is if pi is the radius. This is unit perimeter, which is half pi. And get 2 very important to understand that's half pi. 2 over pi is what half pi, and that will be 0.6. So 1 minus 4 something minus 1 minus 0.63661977. So let me just do 1. Okay, 1 minus 0.63661977 is what. So this has some kind of thing you can measure. So, if you get a minus, you get a minus. If you minus, you get minus something else. So 1 minus 0.3633027 will give you 2 to the equation. If you get this equal to the digits in a same equal below, so that's why I have the 15 decimal model. But it's 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. But you know this 9 for now because the 9 is fine. 9 is fine. This is 9 decimal. So 1 minus 1, 2 ways. 1 minus 0 can give you the other one. You know, if you see, you know this one, and that's why it matters. So 2 over pi. Now pi minus 2. Pi divided by 2. Pi divided by 2 is what? Pi divided by 2. So this is pi divided by 2 is like a half pi. Similar half pi, but you know it's basically the area half area pi, but it's basically a pi divided by 2. 2 divided by pi. If it was bound to perimeter, this was bound to area. So half of the area will be 1 over 1 minus. 1 minus because you know divided by 2. 1 divided because when you minus you can divide. When divided you can minus. We get the opposite. 1 over 570 right? That'll be 1 minus 1 point, and that 1 point basically 1 point. Let me do 1 minus 1.5707. This number is very important to keep 96 uniform. So I'm gonna keep 9 digits of this 9 digits because you know it's so 1, 2, 3, 4, 5, 6, 7, 8, 9, and that will be because you got divided. I have to divide by the other one. So I do so if I do 1 divided by this, I'll do the other way. So that'll be because if I start with pi. That'd be if pi is the pi is what 3.14. I'll do 1 divided 1 over 1 I have to flip it 1 divided by 57057 divided by pi. That'll be divided by pi. That'll be minus 1 570884693. 332. You know, that's one way. But you know, get the one we could get the multiplier system. So this is half pi. Now we get pi squared. This is a pi divided by 2, and then get the pi squared. Now pi squared is what? Pi squared. So you get pi divided by 2. and get 2 pi. So if you get pi squared, you get pi squared, you get pi squared. So you get the model here, pi. So you have to know these things. You have to keep pi divided by 2. Quiet! So you get pi times pi, or pi squared. And that will be 9.86960444010. But this pi squared is like the area it covers, but you know, get 2 pi, get the other, or the perimeter it covers, the minimum perimeter covers, you get the area 4 pi. This is a 4 pi, what? You get the unit pi, get the unit area, get the what? Compute over there. So you get the unit, get 2 pi. Basically, you have to compute all the dimensions you can access. Basically, unit model and the full scale model. Let's say that I'm trying to do pi squared, 2 pi squared, 2 pi over 2, 2 pi, 2 over pi what? Pi times 2. Get this model. That's the perimeter. You get to 4. Okay, get one half. But we got the other half of the pi. But you know, this is a half unit, half perimeter. But you know, get a full perimeter. That's your point. So that'll be pi. That'll be 3.14, 3.1415. Because I can't remember pi. So that'll be pi will be 3.1415. So this is a table you need to ensure that the coding never breaks. You know, because you know, if you get something like breaking this, you know, you get you know, so I'm gonna keep this aside. You know, this is the model I've got. So this is what I'm trying to verify at the local maximum, local minimum, and the maximum. You know, based on half of the system. So you may not understand this, but this is what my situation model for my local OS. M for Mike, U for umbrella, K for kilo, O for Oscar. GitHub.com//O for Oscar, B for Bravo, I for Indigo, N for November, E for S for X-ray, U for umbrella, S for Sarah. This is a Muko OS. So that kind of idea here, you get it. So it may seem counterintuitive, but you know you can. So this matter what it says you're using. What's the medium of wave? You know, there's no they can construct them. So zero construction that's in temporary, the full way, the full half, and a full perimeter to compute this pi, and that'll be 64%. So 2 over pi is what? So basically, I'm gonna use the numerical equivalent of it now. So 2 over pi, because I'm not done with it. I have to get the table correctly. Because if I fail this test now, I fucking written up. You know, 2 over pi is what? And then times 100, and that'll be because you know 100 is stable. That'll be 2 over pi is what? So you have to get the 2 over pi is 64. So 3 so I got 64% here, and that'll be so you get 64%, and you get the opposite one. That'll be 24 26 4 26%. Then we get what? Because you have to go to get 56, 57. You get 58%. So you get 58% here. So 58%. You get 58 minus what? And you get 2 10 2. 10. I'll get 42% because 58% you get 86%, 87. No. 87. 87% here because 9.86 pi squared, 9.869 pi squared is 89. Oh, it's 87 plus 3 and is 10 carry the 1, 10 get 30%, and then pi is just the full one, but pi is like has the opposite 1 over pi. So if you get pi, get 1 over pi. So this is just pi, but 1 over pi is what? 1 divided by pi, 1 minus pi. And that'll be 1 minus pi. Look, I don't want to talk about pi, but you know, but pi is just 1 over pi, 1 over pi. You know, just to form the perfect circle. So this is like a 1 over pi. So get pi is just basically no matter the medium, you get 1 over pi. So 1 divided by pi is what? Pi. Pi. So you get 1 over pi and get pi for obviously you get 0.3183098 square, but you don't get pi squared. The pi times pi. So you get 1 unit of pi, and then that's basically this 10%. So this is 10% we're gonna try to do because you know, 1 over pi is like a 1/4 over pi. That'll be 0.6. Basically, this 1%, and this is pi 100%. This 1% is the 0.3163098886183 minus 167. So 0.33183. I don't know. I think I'm gonna run out of space. Look, okay, guys, I'm gonna stop this recording so I can upload it. I'm gonna start the recording, okay? Upload this, okay. So, I'm just starting to go 0.186 because you know it's pi divided by So I move on to the thing, because that'll be 0.13, because it's just the 1% of it, because 1 divided by 1 divided by pi as well. It just gives the unit pi, which is the same thing as 0. Look, I don't know time, but you have to do this properly now, because if you fail this, you'll fail everyone, and we don't know where we're wrong. So this lambda calculus is like that's why it's important you do it properly. Calculus is good, like 1 over 0.318. 986, So basically, get 1 over pi will be 1 divided by pi. That'll be 0.3, so it doesn't matter if you make one mistake, guys. Mathematically, this has to be perfectly got every single time, so we don't mathematically make a mistake. If one takes a mistake and it proves the mistake, guys, this will fuck up everything in production. I'm sure that it doesn't matter whether it's African or not. So this is very important to understand. It's here. So this kind of framework of pi. So this kind of the kind of say, especially the bottom one, the one because the chemical start of anything is 1%, but we will share 1% literally in everything we do, but you don't know it. If you have the first shoes, okay, so I'm trying to formalize this properly. So let me just save this like literally, because like I'm trying to stop this now, because I'm trying to go export this. Pi 3. I'll get pi 4. Pi 3 less lecture, because I'm trying to update my Moodle journal. This is really get pi 3 and get the file new. Basically, I'm using Audacity to do it now. Let me just, we have to do this kind of things I want to hate, automating, because I should do some work. So I have to start automating Python, so you got that so one thing is that you got this kind of series of this, like the kind of signal, everything signal that propagates in the medium digital space and the analog space share this kind of framework of parallelism, via signal processing. But they get the so if you get 1 over sine, which you call the arc sine, because the arc sine lets you see the opposite. So if you get a sine, if you get an arc sine, you're computing this. All of this, but the opposite thing, so you get the arc sine, and you get the arc cosine, and what you get the arc tangent, but the arc tangent is like the z, but the z is seen, or your z is seen my y, but it doesn't see my x, so it doesn't see my x reality, but it's just it will be half of my y, which is my full y, one y axis. You see one axis, but it doesn't see my whole axis. You just see one y axis fully, but it's not seeing or 2 half of my y. So number 2 half of my y. If I get y, you only see one set of homogeneous data. You're gonna get 2 axes of homogeneous. You're gonna get the full picture of my y, but you can guess the opposite and know the opposite fully. Which is why it really matters, it's just, but you have to use some extra, you have to use expensive resources. That's the I don't want. So this one's saying, guys. So you get the arc sine. So you get everything that's a sine equation that maps from 0 to 1. So sine. So you get the sine equation. But the sine equation is literally. So you get a sine. So the question. So the kind of idea I'm trying to envision is you get a sine equation. The sine is what rise of run. The sine takes a number that's 90 degrees. But this signal can probably be so we get 90 degrees. We get a sine 90. We get sine 0.5. But you get inverse. So you get so you have to put in what a fraction, which is like the sum one use. You don't have to put 90 because 90 because of rotation is like polar. So if I put 0.5, it's half of anything I have. Anything you have, so that's the same as a half of 90 degrees, but you don't know 90 degrees, you don't know whether to turn right or left, and that's kind of the ambiguity of it. You don't have to put that kind of ambiguity. That's what I'm saying. Polarity matters. If I say half, turn halfway, half is either half of my direction, but that half of direction is 6 o'clock, because 6 o'clock is half of 12, of my 12 o'clock clock is what 6 o'clock, but if it's danger, if it's a lot of danger, 6 o'clock just means my 6 o'clock, my right. Because just think, oh yes, my right, this is my 6 o'clock. That kind of intuition I'm giving you guys. Because if you look at a shed, if you like kind of this kind of wolves in the dungeon, if it's a wolf in the park, if there's a wolf in the park, and in the park at night you go for you're in a park at night, you're a werewolf, or you go for a park, you go be hunted by a pack of wolves. What would you do? Turn right. Turn right is a shed. Don't turn right. Doesn't matter the danger there. That you're trying to get the safety, and that's what I'm saying today. It matters because your safety of turning right is like you go right 6 o'clock. 12 o'clock, 12, 6. So you get 12 or 0 or 3 or 3 or 3 hours 3 hours 6 hours and 6, 7, 8 hours. But the 9 hours is what? Yes, you get that. Then you get 0369. So it's really that's kind of day. So it doesn't matter where you are. You know, we have two axes of time, and that's 45 degrees. We share equilibrium of a half of 3. Obviously, your half of 3 is my. So basically, don't forget to your half or 1.53 is basically when you say 1.5, 1.5. That means rotation right. Right, I see left. I see that's why 40 doesn't matter. So basically everything is a half. So if you have 90, you see 45 you're looking at. We share 45 degrees. So if you rotate half or something, you know, you're rotating half positive, half positive. You just have to find how to do that thing, and that's what really matters here. Let me try to get another paper. This is like the ugly one, Namdi, but this is what you did. This is basically we're gonna try to use the computer again. But you know, so we share 45 degrees. 45 degrees access. This is like another one. But you know, we share 45 degrees of the full path and width. So just like a session continuity of the system. Let me get a new paper now. So we share a half of everything. You know, whether you like it or not. You know, that's what it says. The point of it is you share. Whether you care for it or not, it doesn't matter. But we share it. You know, if you're in the public world, if you're public, you're public, you know, it doesn't matter what energy of wave. You should share it. I'm trying to get my pen. We get people. Oh, no masking no more, guys. No masking, guys. I love Andy. Andy's a beautiful woman. Andy, you're a beautiful woman, you know. Almost beautiful, you. Oh, Andy, you're fused, Andy. You're just fused. No matter what is a fuse of lightning, it's like literally that. Because it matters to you. So 12:6. I'm not using my clock analogy. 12, 3, 6, 9, 12, and then we get so it doesn't matter the path we take. So your start. If we start at so if we are at 0, 0, basically we are at where? Northeast. So if we are at 0, 0, 0, 0, 0, 0, that must mean we start to go somewhere. But this can be anywhere around the world. You know, this is our end. This is our end. So if we start as 0, 0, my 0, 0 is your my epsilon. We'll start at epsilon. Epsilon. We get 4 epsilon. We get to epsilon, which is 0. Because I don't want to write in the epsilon 0 because you know that we share 1 over the axis. So we have a trident axis model, but it's like the genome thing encoding. It's very important you look at this formally. I think. So for example, your 3 o'clock is what? My 3 o'clock is what? My 3 o'clock is your what? 2 months. So 3 o'clock be. So if I start 0, this will be north, south. So south to the power 4. Because you get 2 4 south. So you have 4 south because you know that's one path you take. So you get 4 south. But your 4 south is really we have 4 north to the power 4, and then we get south east to the power 4. But east to the power 4 is a start and end. So we get a start state of east and start and end because you know depending on where they go there and coming back, you know, and that's the point of it. So you get an epsilon state. So we get an Eulerian upper epsilon state based on the formal Cisco model of north, east. We get for every direction we have, every way there is, every way there is to be. For us in our physical form, we have what e to the power of 16. Because why? Because you know, you get 4 plus 4, which is like the way we go, north, and we get the direction we gotta go, which is that's what we need because we get 16. So that will be 4 cubed. 4 we only share in the physical location. Thank you, Annie. 4 squared. Thank you, Annie. And the 4 squared is what? 4 plus 4, and we get 4 to the power 16. Minimum. You know, based on the direction we're gonna go. Whether north or south or east doesn't matter. Because thank you, Annie, for calculating. I love you. If you had the space and time, I love you. So as I'm saying, guys, we share all that thing, but so if we're going together, if we're going safely together, but you know, if we get there safely together. So the idea is like the spin of the quantum physics is like an different form of quantum physics is like it's an issue to stability for children everywhere. But the bunny, the kind of a bunny concept, you know, bunny go anywhere, but then they always safe, you know, keep the bunny safe. I don't want to get to die, but the bunny to die, you know. No matter when they come, they can go safely. The constitution, if the bunnies are there, we should get bunnies there. They follow the bunnies are safe, you know, because that means something is actually happening in our biome. You know, we want to see the bunnies. You know, it doesn't matter whether you're a tourist or not. A tourist or not, never a tourist. So north start, north end, north start. We share tripolar state. If you're not sure, but one on sure. So we're gonna leave that out. for the encoding. So start and not sure. We're gonna leave that out for the encoding for now, because that's the nil state, mechanical nil state. That's 4, because we don't know where we are, in the world. But we're gonna just compute where we're gonna go. So basically, this can fold, because you can see all the dimension. When I fold this, you can see half the reality, which is can not know. So you can see how we can fold this dimension. So you can see how say I can just now fall down. This one with basically oh my days, Andy, you're right, Andy. Our ratio fold is 90 degrees, and we fell down here. That's why I cannot go up. That's why I cannot climb with my legs up walls, Andy. Because literally, I thought basically our ratio. I don't know. Basically, we had a big gap in our reality, and basically, we had a gap, some kind of way, because we're moving away from other dimensions, But literally, because our relative folded in itself, it had a big crunch. Our domain has a big crunch. Somewhere a big crunch happened. Something imploded itself, and then relative started to fold itself. Because if you see, so I'm saying that in our reality, something imploded first, but away from us a long time ago, like decades, years. We didn't even know it happened. But that imploded, something imploded on us. But that affected our reality. So imploded on us, that means okay, something exploded. Sorry, Andy. Something exploded or imploded. Thank you, Andy. And then we faked that we became what? Created. So we become created, and then we never died. So because we forced to be created, what? We crunched. Which halved everything. Our space and time, our reality, our form, everything in this universe is half. We can see half, we can feel half fully. But we are, because we already won, because this exploded, imploded. So if you create let me try to think here, Andy. Let me try to get it. Read, write, execute. Read, execute, okay, right. Because everything is executed on the fly. Read, write, execute. Read, write, execute. So 2 reads equals 1 write. Is 1 write. 1 write is 1 read. 2 writes. And it gets 2 writes is what? 1 read. 2 writes equals 1 write. 2 writes equals 1 read, because the share calculation says 2 to 1. Guys, I love you guys. So this is what I'm saying, guys. It doesn't matter what it is. Everything's on the fly. And that's we have quantum physics, because 2 writes equals 2 reads, and 2 writes. You don't have to execute anything, to read it, right? Because you just have to change the state you are in. And it doesn't matter how you do it, and that's kind of the hacking of the relay system. So that's what I'm trying to mitigate. Thank you, Andy. Andy's ahead of time. He's just thinking of his own, 2 writes. If you have an R squared, you got the whole R squared. So you have the whole spectrum of R. You can get a sequence. You can read an R. You can just observe a reading state. You can relay that reading state 4 times, Andy. You can get it. I take the whole system. Andy. Yes. So basically, R squared. If you have 2 reads, 2 reads, you get 1 write per mission. But 1 write doesn't mean you have full access. It means you write to 1 file. So R squared is 2 reads. 2 reads equals 2 reads equals 1 write. But you don't think about the reads per mission. 2 reads, 1 write, and 3 reads equals 1 execute. So I need 3 reads minimum, but I need 9. So again, let me think about this properly. Let me think about this. 1 read, 1 write, 1 execute. So what you need 3 times 3 to get 3 reads and 3 writes, and that'll be 3 reads and 3 reads would be what? 3 times 3 will be R cubed. 3 writes, so that'll be 3 times 3. To get 3 reads, 3 times 3 is what? 9. Now you get 1 read or write per mission. But to fully hack a GCF system, the full area of a system, 3 times 3 is 9. That's the local maximum. You alone can hack a system, Andy. Thank you, Andy. I love you for remembering this. And then you get 3 times 3 is 9. And you get 3 plus 3 is 6. So 6 to 9 is the stability equivalent for me to keep the system hostage. So 9 plus 9, 15. So if I maintain the area of 9 of if I'm within the area of 9, I have to keep 6 active states or 6 active nodes minimum to hijack it via the read permission. Because if I maintain 6 reads, 6 writes, 6 writes buffers, I have full access of the full 9 system. And this is full write access control. It doesn't matter when the pieces are observed on the whole system. That's why the system matters basically. So quantum physics. This is what matters. So everything's hacked to me because I already know. So what's done is what's done can be undone. But you have to undo it non-linear via the first series, right? Via one way. We can't do through the electronics or digitally. You have to do it at what do you digital okay. So let me do this now, Andy. Let me do this now. So basically this is my framework. So what I'm trying to compute now, so basically I'm trying to figure this out, Andy. Andy, keep quiet, I love you. RWX, that thing your name, because I don't want to forget this, Andy. Thank you. Thank you, Andy. You're here now, you know. I don't. You didn't cover the area. I know you didn't cover the area, but you are here because I accept you are here. But you know, I don't like this. Never accept you because you know that means something wrong with me, and I don't accept you. And I even accept him, but I don't like his name. Then I don't like his name. It's rubbish. It's annoying, and you're very beautiful. So I'm thinking myself right now. What am I thinking? So the goal of this AI is to be really just hold the space for you where you don't need it, where you need it, where you don't need it. Because you know, if there's some kind of internet, like some my ears, something to hold some kind of physical space for you, where you need it. That's kind of a problem there. What is the UAI? Okay, so what's the problem here? So let me think. So lapse integration. So get So I'm trying to compute two xy's, your xy, your reality, from my xy order. So your minus xy. So I need to go through the state of epsilon. So I have to like get the my epsilon. So I have to get get my epsilon. So I get sine what? Sine x. Now I can do sine x, I can do sine minus x. Or I can do arc sine x. I can do arc sine minus x, and that'll be fine. So this is the four things I need because there are two minimum. So how would I do this? Let me give some of area, and that'll be over 180. Of 180 degrees from A to B, because 180 is like the area of A to B, 2 pi r, and then we pi r squared, and that would be 180. You see. So what would I compute with this, Nandy? The bunny thing. Yes. My security buffer. No. My shell. So this is my one. So this is security buffer. What does that mean? So we get to a point. So you see this point, this is like your standard point, 0, 0. This is where you're perfect. This is where you're 10%. Can go anywhere, but you know, this is where you're 1%. This is where you're 1%. 1%. This is where you start, but you know, you get a 1, 1. So we're going to use 1, 1 to do it. Let's use the numbers, maximum of 10. 10. 10 is the maximum number you use. 10, 10, 10. Because 10, if it's above 10, so 1 to 10 is the maximum range you're going to do to make your state to prove this. So I'm trying to compute this over red. So it doesn't matter what it is, RGB. Colors or so if you have a red, green, blue model, Namdi, you're trying to ensure that this red, blue model, the sparsity of green, you know, or like because you know if you have red, green, red, you get three reds per segment of a screen. Three red colors. Now, 3 red is the same as r to the power of squared because you get the area. So this r to the power of 3 is equal to 3 red, and that's what I'm saying because 3 red is just one cone. Because you have 3r. If it's not a fluid, if it's like a Cartesian system that just displays grids of colors, you know that's equal to the same fluid system you're doing over r cubed. And I'll share the full state of the same thing, but you have to do it with a different digital signal, via digital signals. You know, digital signals, never analog signals, you know, or both. You know, no matter what, via or not. So, via this, I'm still recording this. Is he done? Oh, 21. I got 9:30, so 10%. So if I'm okay now, no social media now, 10% a path. Where you can go, 2 ways you can go. But this 10% is a stem. This is my stem. This one grounded. This was just maybe a point stem, but you know, stem is like just a point in space. So I'm trying to define this properly. So basically, you get to tomography layer here. So this is like what I'm saying in my last video. So you may think here. So this is my model here. But basically, these are the signals are nodes here. But they're nodes because they're important. So I have to fold the node in. So this model is actually this model. Because no, if I take initiative, so basically this is what I'm saying. If I'm stuck here, I can go all the way forward. Because you know, I'm sure I ground that space on time. You know, it doesn't matter what it is. I'm just trying to do here, because it's like about if I get 2 static ones, I am dynamic. So this is me. So if I have a system area, and that is 45 degrees, and that's a half. So sine a half. Let's do this properly, so get this math done now tonight. No one should fail this one because you should sine a half or sine 0.5 is what? Yeah, sine. Wait, sorry. 4 minutes. Okay, 1 second. Sine 0.5. Sine 0.5 is the sine of a half is what? Sine of a half is what? 45 degrees, and that would be sine of a half be 45 degrees the sine of a half of what 0.00875, and this would be half of 90, and this would be a sine what? A sine 45. 5 degrees. I don't just check it. I don't check it. So I just know the same thing is here. But this sine of 90 degrees will be the I have the opposite one of the Cartesian one. Will be the arc sine. So the arc sine will give you the same because it's late now. I don't want to make sense. So the arc sine will give you the inputs. So if you put arc sine, if you flip this over the arc sine, divide this by the arc sine, Oh. So okay, let me just do 1 over sine. Let me do 1 over sine because it should give me the same thing. If it doesn't give me because fuck off, 1 over sine, 1 over sine 1 over sine 45 degrees. 1 over sine because you know as you compute. If it doesn't compute because it's 1 over sine. 1 over cosine. Sorry, this is just the y1. This is the y-axis. This is 2y. So if you want to do 1 over cosine, that will give me the x-axis. 1 over cosine 4.45 or 0.5. No, 0.45. Sorry, 0.55. 1 over cosine. Okay, let's do 0.45 because 0.45 is 45 degrees. I'll do 1 over 45 cosine. Thank you. 1 over cosine plus 5 will give me 0. So I mean, cosine. So get the cosine 0.9993. But so you get 2 ways to do it. So I'm trying to give you the area. So the area of 2 parts are really just 2 ways you can go. For 5 degrees, 2 ways you can go. Over 45 degrees, or half of half. So that'll be 1 over 4, 1 over 2, or 1 half is what? 1 half of 1 half is 1 over a quarter. And so we get 45 degrees divided by 2. So you get 90 degrees. 90 degrees, you get 90 degrees. You get 90 degrees, you get 45 degrees. And my goal is really just to do it now because I'm gonna go up. So get like this way. This is what I mean. So get 45 degrees. 45 half of 5 degrees. 45 divided by 180. 180. That's basically from going back and forth. So I take the same part 0.25. Now 0.25 is 1/8 of 45 degrees. So if I can go back and forth, I take a calculus. I have 0.25 to go. Now 0.525 is can go 0.25 plus 0.25 and then complete 1/8. So I don't even want to think about computing the 1/8. So this 1/8 state is already in there. That's why I don't want to observe or I don't want to know. But I know if I can compute this, someone can compute it for me or send it to me. That's what I want. Or send it to relay it to me. But if I get lost, if I'm not sure, that is not sure from. So 0.25 is 0.25 is a half of a half. 0.25 is 1/8, 1.8, 1/8. So 0.25 sine would be from the east from if I'm going to the east, if I'm trying to go to the east east. So that basically going right. So if I go east once, that'll be me starting from where the north. But I'm trying to go from the north to the east. From the east, if I go from the east, if I start from the east, if I east start, if I go east start, that'll be east, that'll be east to the west, east to the east northwest. So if we go to the west, that'll be east. One east will be what? Pi. That'll be 0.25 times arc sine. So that'll be 3 times 5. Wait, yes, it's fine. 0.25 times pi times what? Pi squared. So get pi squared. Pi times pi. Pi times pi is pi squared, and that'll be 9.86964. This will be cubed, squared. But I can double this out. 9.85 will be 5%, a stable 5, 0.5. So 2 I already know this without thinking about this. And I go right, so I'm going to go right, but not left. So that'll be this will be one left up, one left x, one left my view, one left one my plus x, looking right. Because I'm turning left from right to left, right to left. So I get from right, I'm looking left, but I'm trying to go 2L. So if I go right again, I'll be at one state. I have to double this. So that'll be 9 times 2 plus 2 plus or times 2, same thing. Yeah. So if I go once, so I'm now at 19 degrees, 19 and a half or 3, 9, 2,
392.880/21. Now I can either take this and copy this full one, but I can shift my plane of existence, my plane of understanding, because I know more. But so I can observe more of my reality. So I never need to. So I just copy this data. So anything I can see in the area is this, via units, because we started from 0.25, and that will be 19.7, and then that will be the squared area. Now that will be divided by 180. Once you give me the free list from A to B, but I don't want to do 180. I'm gonna do this. Let me divide it by 180. We'll divide it by 180. So this number, we divided by. So this number 19.739208802178 divided by 180, going from my start A to B, will be 0.110 0.10 711,273. But this is like the kind of the unit I cover. So that is divided by 180 because it moves from A to B over the polar axis, pi squared. So this is pi squared. So pi squared over 180. This was also computed just for me alone. So this is my pi squared. But so let's get their pi. So I'm trying. So if I invert this, if I invert this sign, my pi squared, this is my pi squared. But if I then do 180 minus it, there's a plus of it. So if I do, let me just copy it down properly because I can't use it properly now. If I lose, I fuck it up. So the number is 0.10662271123215095. This is my 180. This is pi squared over 180. Now, this is 180 over pi squared over 180. Now, I want to get the opposite one, which would be flip it. So this would be the arc sine of it. So if I get this, I get the sine. This is my cosine of it. So this is the number I need to go because I have to get the cosine of it and the arc cosine. But the cosine of this is a number. So what do I use? I use the I have to concentrate. So I use the cosine. If I use a cosine, I have to get an angle. This is not an angle, so this is not the way to put it. So I put it into arc cosine. So I get the arc cosine. So I have to put trigonometry. I have to go to arc cosine. This is the cosine. Basically, but the cosine is 1 over the cosine. So I divide by. So I take this number. I copy this number. So I get the 1. So I get 1 over cosine. Cosine this. So basically, let me just try and calculate the arc cosine of this. Arc cosine. Arc cosine calculator. I usually put this number in. Basically, arc cosine of 0.109. 662271232150957, and that'll be 83 the 0.704152 646 degrees. So basically, if I hold this state in unit, this is my this is for 10%, and this means the system is stable over the area model. So basically, it's tracking the state, but it's tracking the area. That's why the integration matters. Basically, it's Laplace integration via the. So if I have the area, if I have 1 plus 1. If I have the units a full 1, I have a full half. If I have a half squared, that's a full area of 1. But that full area of 1 is the rotated right, left. So this is the inverse of. So basically, I basically get this integration of Fourier series. No matter what is algo single, I get if I for the two right integrations I take. The two right integrations, I have one full left integration, or left algorithm I can do, a function I can take. And you can see I've got it now. So this is arc cosine, which is 1 over the cosine, and 1 over the cosecant is like the same thing, but it's the cosine is so you got a secant, which is like the so over tan, y over x. But that's the final one you need to do for your stability, for our local stability. So
You see there? So I'm saying, so the function is context switching. So it doesn't matter whether the parser do context switching. The integration of the system is this one space and this one time equivalent to that space, and that's why this really matters. What I call the Lapis left integration rule, 10% because it's sustainable for the parsers. For Rift, via metadata mref or metaref files or .ref files and .ref, we share a calculus set of .ref for polyglottic TOML files for Python, whatever the build target is for the target language. Because you can use the standard ref files for the packaging. Rift is a floating target, but they have the only culture. But you use the Rift or the TOML file or Python Rift or TOML, which I can show you, or the standard package or Lua Rocks package manager or C's or Canon. Doesn't matter the package manager. It's just Rifting, and that's what I'm trying to give you guys here. So basically, I've just showed you guys how this works. So guys, look at it. So picture guys, I'm going to show you guys my work. It's really important guys to see my work. 1, 2, 3, 4, 5. It doesn't matter basically if anything is loading. I don't want anything to be loading because loading is bad. Because loading is bad. It just means we are inefficient. But everything has some space. It needs, so it's preloaded. This is because just loaded because it's there. Because I'm trying to encode myself into reality, but in the metaphysical sense. So man, most simulators literally just anti-pop protocol, so you can never pop because you have the space and time at one time. Because what I'm trying to really do is this. So basically, I'm trying to smooth out these edges, but I'm not trying to smooth it from the side. I'm trying to shape this into some kind of curve. But to shape this into some kind of curve will be the flame. So this is a little pointy end, because this is a pointy end. So this pointy end is protected. But for this to be protected, it has to be bubbled. So you get this axis. So if you get this axis, you get the lapis can go up and down. You get infinite dimensions of the same axis. But the goal is you start from where you start. You are shaping with a care. You are. So if this is a point of A and B, you get a path. This is you here. If you're outside, you're not safe. But you are inside. When you're inside some kind of topology, you're safe. So you get a Bunsen burner. You get a thing of dynamic effect. If you go into, it's like a bubble, but it behaves like a water. But if you're partially different equation, you're solving. To show you're safe at the space and time. You need to be safe. When you need to be safe, you need to get safe. Because it's when you have a red bulb, when you have a red flame, it's not really dangerous. If you have an orange flame, it's more dangerous. And you're getting in danger. If you get a green flame, you're burning. You're already burnt. It's already dead. And you get red, green, red, green. Thank you. But you get the red, orange, RGB, red, green, blue. But the blue means you're moving away. So that's blue shift. So something is in danger and you can signal danger without actually being told there's danger. That's kind of an encoding program I want to do. It doesn't matter whether it's words or something. The language means danger. Basically, it's a danger problem. It's kind of the symbol that means danger. Based on your ontology perspective, it doesn't matter if it's a heart or something. But that's the problem I'm trying to solve. Because we have a kind of cool color state, and that's why I'm having a mesomic because the color state is mesomic. This matter the medium you use, we all have a shared medium. In that medium we all use what is it, pen and paper or pastels or ink. That's what I'm trying to say here, guys. Okay, thank you guys.